Welcome to Module 56, Other Forms of Learning. This is going to be our last real contentful module of the course. And we're going to just pull on a couple of threads that have yet to been covered in the rest of the course before we move on to the final review subsequently. I should mention that, this particular module is going to be pretty brief. Despite the fact that this course has been pretty packed with information, we've only scratched the surface on a variety of concepts. Machine learning and artificial intelligence generally really is one of the richest ecosystems in science, in my opinion. So even though we're going to go pretty quickly over some of the core concepts in other forms of learning today, I would really recommend that you explore things with your curiosity and take your adventure where it leads you. So, imagine we're building a support ticket triage model for a company. So you're at a company, you get tickets from your customers for support, and you have 250,000 historical tickets from the past in text. You have, of those 250,000, you only have 1.2 thousand human labeled examples. And we know from some statistics we've been gathering internal to the company that labeling cost is exactly 2 minutes per item. So it means that just if we wanted to label just 10,000 more items, which is still a small fraction of all of the available data, this will take about 20,000 minutes, which is roughly 333 hours. I recommended at the beginning of this course that whenever I make arithmetic errors, you should let me know. So feel free to always check these numbers that I'm giving you. But it's a long time. 333 hours is a lot of time to spend labeling at a company, especially a small company. So our practical question from a real world perspective is, well, can we get more data? And deeper than that, it's can we get more useful supervision without hand labeling everything? Okay, so we have lots of issues available to us, and we can always get more data, but we need to be careful with what data we get and how we go about labeling that data. So that's the kind of the framework for today's module. By the end of this module, you should be able to explain why self-supervised and semi-supervised learning are attractive for this kind of situation. You should be able to distinguish between these forms of training, supervised, semi-supervised, and self-supervised in situations where you have some supervised signal available. You ought to be able to analyze cluster and low density assumptions. This is going to be a bit of a stretch, but we'll see this related to how data points cluster together and how that can affect these kinds of learning methods. We should be able to implement a very simple pseudo-labeling or consistency regularization baseline. So I'll give you lots of code so you can just replicate this yourself. And you should be able to justify when a self-supervised pretext task or pre-task is likely to help a downstream task. Pretext tasks are not always called this. There's lots of different names for this, but it's basically a task that we do once beforehand. It's like a pseudo task that we run on the available data before we go and do the task we want, which is, say, the supervised classification or regression tasks. So here's the overall picture. Of course, this uses a library called Mermaid, which has this effect that it works well on one computer, not the other. Hopefully, this renders properly in your computer. But basically, we have a situation where we have raw data. We have many examples. Like we have a ton of data, like we had in the previous example. We have to ask ourselves, do we have labels? If you have many labels available to you, then you can just go ahead and use supervised learning. If you have a few labels, like a small number of labels, and much of your data is just unlabeled, then we'd go to semi-supervised learning, and this would lead to kind of joint supervised and unlabeled data objectives. So we'd have two objectives being learned at the same time, and we know how to train systems with two objectives at the same time. We've seen it over and over again in this course. And the third scenario is you have no task labels, but there's a lot of structure in the data that you can exploit. So we're going to make some transformations in the data. we'll use those transformations to learn representations, and then we'll use those representations to fine-tune or do probing or do some transfer learning that will eventually be the supervised, the replacement for the supervised task at the end. So it's not going to be the case that self-supervised or semi-supervised are necessarily more advanced versions of supervised learning, although that they are technically more complicated. It really, what we're really trying to show here in this differentiation of these three types is where the training signal comes from. In supervised learning, the training signal comes exclusively from the labels we have. We have lots of labels. In semi-supervised learning, the training signal comes from a mix of the actual labels in the labeled examples in our data set, and some structure in our unlabeled data, which we can get from like the similarity or like clustering in the unsupervised unlabeled data. And in self-supervised learning, we have maybe no labels at all, but we have some basic structure, and then the training signal comes from modifications to that training signal. We'll see one example of this in example 2 in today's worked examples. So here's another view of what we just mentioned a moment ago. Here's sort of a decision heuristic or decision tree. So we will need a model for some downstream task, and we ask ourselves, well, how many trusted labels do we have? We didn't talk too much about the nature of trusted labels, although this did come up around the middle of the course. But imagine we have like the concept of we have a ground truth and we gold standard labels and we trust them. If we have enough of these, we can go ahead and start supervised learning. If we don't, we only have a few of these. We might ask, do you only have a few like unlabeled data? If you don't have enough unlabeled data, then we're going to have to go ahead and collect some labels, or simplify the task somewhat, which is a bit of a science fiction scenario in which we can always rely. Otherwise, we can define some like user, like some special pretext task, or augment the data in some way. And then we can try self-supervised learning or semi-supervised learning and then fine-tune afterwards. So fine-tuning, or what would I call fine-tuning or linear probing is sort of the last possible step in the self-supervised or semi-supervised training branches. So here's a little rule of thumb for you. I should have put a call-out box around this, but there we are. The rule of thumb is we'll use semi-supervised learning when the unlabeled data should help the same task directly. So there's unlabeled data, but the unlabeled data is still useful to us. It still clusters in ways that is useful for us. It helps us solve the task kind of directly. And we do self-supervised learning when the unlabeled data can help us learn a representation for what that data are. We're going to learn the representation of the data, kind of not too dissimilar from encoding from the previous few modules in these encoder-decoder networks. We're kind of learning a good representation of the data. How do we learn a good representation? Well, we perform some transformation on that data. We used masking before, and we'll see it again, and we'll see another example of transformations. But you can transform the data in predictable ways and then use those transformations to learn good representations. That's self-supervised learning. I'm learning from myself. Just a few precise definitions. So D sub L is the labeled data set, and D sub U is the unlabeled data set. So in the labeled data, we have N sub L examples, and each of them have like the input data X and the labels Y. Unlabeled data is, we have N sub U examples of that, and we have just the inputs there. We don't have the labels. So we have the raw measurements, but we have no gold standard ground truth labels. So given this, we can use supervised learning and only use D sub L to just learn the task X predicts Y, like we've been doing a lot during this course. For semi-supervised learning, we're going to combine DL and DU kind of side by side, but separately, and we're going to train them both towards the same downstream task, like we want to classify the data. Self-supervised learning will first create a training signal from the data itself, and then we'll use that training signal to do supervised learning afterwards. The training signal can come from masking part of the input and predicting it. So we saw this a little bit when we talked about transformers and encoder-decoder networks. We can reconstruct a corrupted input. So we could add noise to the data, and then we could train a model to remove the noise. That second model that learns what is noise and what isn't noise can use that representation to kind of understand the nature of the training data, even though it's unlabeled, and then it can use that representation for some downstream processing. So we'll see an example of that in worked example 2. And then you can also bring two views of the same example closer in the representation space. So this is one type of contrastive learning, and we're going to see an example of that later in this course, in this module as well. So again, it's a helpful distinction just to help hammer this home a little bit, because the names are so similar. Semi-supervised asks, how can unlabeled data help the supervised task directly? Self-supervised asks, how can I learn useful representations before I even have many labels? One heuristic that I have that helps differentiate these two, again, it's not too difficult a differentiation between semi and self-supervised learning. Semi-supervised, you're learning from a little bit of supervised data and a little bit of labeled data and a little bit of unlabeled data. You're combining these two things together. It's kind of half and half, so to speak, even though you probably have much more unlabeled data than you have labeled data. It's still kind of a combination of two things, so we call that combination of labeled and unlabeled data semi-supervised. Self-supervised learning is really you're using your own signal and your own data to understand a good representation of yourself. This uses the same kind of language that we saw again in encoding with transformers, so that's self-supervised learning. And hopefully that distinction is clear now. So here's 3 common patterns for this breakdown. Again, this looked fine on my other browser. For some reason it's not showing nicely now. Download the slides, hopefully it'll work nicely on your screen. So we have our input. We can pass this through either a corruption, so we add noise to the data, or we can mask part of the data. So we remove a word from a sentence and try to predict it from the words around it, or we black out a section of an image and try to reconstruct the pixels in that masked out region of the image, same concept. Or we could take a data point, augment it somehow, and then all of those modified data will be passed through, either predicting a missing part or removing the noise or matching the two views we just augmented in the last idea. All of these tasks are more and more performant. Like they get, the better and better they get, the better and better they represent the data, right? So the better they are at differentiating noise, which we've explicitly added, so we know what is noise and what isn't. The better the model is at removing just the noise and then reconstructing the original, which we kind of have as kind of a fake label. The better it represents the actual data, right? Similarly, we have the actual full image. By masking out part of it and removing it, the held out part is sort of like a pseudo-label, right? So we can take all of the other data, that's kind of our input X, use that to predict what should have been in that masked out area, which we can pretend is Y. We can compare it directly against that little patch we removed. So it's kind of a supervised signal in some sense, except the supervised signal is just the image itself. And then doing that also gets you a good representation of the image, because if you understand the scene, you know what that missing piece should look like. Or if you remove a word, that removed word is sort of like a training signal, like a label. Given all the words you have, which is kind of like your X, you can make that prediction. You can actually compare what it predicts against the truth, so you have kind of a pseudo-supervised learning task. But it gets a good representation of that missing label. So all of that's great. We have it. We saw that several times already. We just didn't call it self-supervised learning every single time. So we have a task loss. We have for this problem, and then we can have we have our representations. We have possibly some unlabeled samples. We can get consistency measures, which we'll talk about later. We have our labeled subset. This is like the data set D sub L, which I mentioned a moment ago. And we combine, the labeled data if it's available with the representation if it's available with the consistency pseudo-labels if it's available into the overall task loss, which can be a combination of multiple terms. So self-supervised learning, does its own thing sort of thing until it learns a good representation Z. Semi-supervised learning combines the good old task loss, like the loss, like the cross-entropy loss for classification, with some other unlabeled data loss, and combines them together with like a plus. We'll see that soon. Sometimes it does it in sequence, sometimes it does it in parallel, but that's sort of how these two modes operate. There are some assumptions here. I was going to find some individual citations for each of these points, but it became challenging to find appropriate separate BibTeX or citations for each of these, but regardless, you can take it as read that for this to work, for this sort of augmentation or the self-supervised learning or the semi-supervised learning to work, we need to have certain assumptions about the task structure and about the nature of the data itself. And this is sort of maybe more like common like rules of thumb or common wisdom. So we'll need clustering assumptions, especially for, including for semi-supervised learning. So when you have points that are in the same regions that are highly dense, so a lot of points in your overall data, in particular here, the unlabeled data, D sub U, all of those data in that high dense region of lots and lots of data points should probably share the same label, right? So we've seen lots of visualizations of data and data points strewn over the space. High dense clusters of data should probably be labeled the same way. That's one assumption that's not always true. Low density separation. So you might have data points that are far apart from each other and a kind of a gulf where there's very few data points in between. So this is a good decision boundary between these dense regions of data. So it's nice to draw a nice decision boundary between them. We saw examples of this in some of our supervised training examples from the earlier modules. This isn't always the case either. Sometimes you can have data points or clusters that are like basically overlapping each other, no matter what view you take of the data, and you have to draw a boundary between them. So the fact that the idea that classes should separate in space from each other is not always true, but this is the second assumption, is that we want that to be correct. The third assumption is this augmentation invariance assumption. So we talked a lot about label preserving transformations and how these label transformations should not change the prediction very much. That is to say, label preserving transformations should not change the prediction much. I'm not sure exactly what I said there, but if you make a transformation of the data and you retain the same label, so you have a new data point which is fake, synthetic, and you want to have the same label on that synthetic piece of data, the predictions you're making should not change very much on that augmented data point. And then the fourth assumption is that this transfer assumption, this idea of transfer learning. If you're doing this pretext task, like this early task beforehand just to get your ducks in order, so to speak, then this is supposed to force the model to learn features that are going to be useful later, right? So that example of like blanking out a section of the image and then trying to recreate the pixels that are missing, or blanking out or masking a word and then trying to predict what word should be there. That's like a pretext task. I'm doing it for its own sake, but doing so should be able to be useful. Like the features I learned from that task should be helpful for me later. If it's not, then I'm kind of wasting my time. So yeah, if these assumptions fail, then the unlabeled data can actively mislead the model if you're not careful. So you're always going to have to double check everything, like we've talked about endlessly in this course. So another anti-example, imagine we build these pseudo-labels, like we have data points and we assign these sort of pretend labels for an image, medical image classifier using high confidence on an unlabeled hospital data set. This is a bit of a preview for an example we're going to see pretty soon. So imagine you see like images and you use a classifier to make predictions on those images. You so far don't have any real labels on it, but the classifier you're using is really, really confident that this image should be labeled fracture for like a bone fracture, and this image should not be labeled as bone fracture. And it's so highly confident in one of those directions. If a model is 90% confident, so to speak, that prediction is one thing or the other, then maybe that's good enough for us to say, okay, the model thinks it's a fracture, so I'm going to think it's a fracture too. Okay, and a lot of times that actually works really well. In fact, we're going to see examples in one of the worked examples in this module of this working pretty well. Not perfectly well, not as well as it usually does in real life, to be honest, but fairly well. So usually this assumption actually kind of works, but like always, there's always these pitfalls, these complexities related to this machine learning process. First of all, if the unlabeled pool comes from a different scanner or population, then you have a data set mismatch, and what you're making predictions on in one scenario might not automatically deploy well in the other. Models can be confidently wrong on minority subgroups, which we've also seen several times, but like just because something is very confident doesn't mean it's correct. I don't mean to anthropomorphize these models, but increasingly these machine learning models are behaving more and more like humans in some sense. And we all know humans, either personally or in the media, who seem extremely confident about some things, but are almost entirely wrong about those things. So confidence is not the same thing as correctness. I wish more people understood that, but that's another topic. So things can also go wrong if we treat all of these transformations as label preserving when some of them are not. So if we're making transformations for the data, and we expect them to preserve the labels after the transformations, this might not be the case. And if you have a small amount of label data, and then you take all these predictions from the model that are highly confident, maybe you have, hundreds or thousands of times more unlabeled data than you have labeled data, and of those thousands of unlabeled data, at least, I say hundreds of them have high confidence from the model that's making predictions on them. If you add those hundreds of labels over maybe a few dozen examples labeled by humans, then those machine-derived labels will override those produced by a human, and they'll drown out whatever signal we can trust. Again, a side note, there's tons of examples now of machine learning doing a better job in making predictions than humans, even expert humans in their various disciplines. This is another problem we're going to have to contend with. But the thing is that AI still makes mistakes in all kinds of ways, sometimes really indecipherable kinds of mistakes. There's still a lot of value for human labeling here, and we can't put all of our eggs in one basket, as the aphorism goes. So, having labels from one source drown out labels from another source is bad. We have talked a little bit about data augmentation in the past, and how we try to keep data augmentation to only a few factors of the size of the original data. So, or just a few orders of magnitude, like maybe 3 or 4 times the size. Anyway, so this is a bad situation if we have this mismatch in scope. So this is a classic anti-example. A lot of people, unfortunately, think that more data is the same thing as more correct supervision, and that this simply isn't the case. So unlabeled data is often going to be very helpful to us, but it's mostly helpful and almost exclusively only helpful when the structure of the unlabeled data, when the nature of the unlabeled data is close to the target task, and also whatever process generated the data in the first place. So the unlabeled data has to have some structure to it which is sort of reusable, if that makes sense. Like, it doesn't matter so much if we have, gigabytes or terabytes of text data from medical journals, if we want to make predictions on like a social media app or something. In fact, as soon as the words left my mouth, I realized that would probably be pretty helpful. But often the point is, usually you want the unlabeled data to be as close as possible to the labeled task for it to be helpful. Just very briefly, this math lens. So this is where we talk about the semi-supervised objective. I mentioned earlier that in a semi-supervised objective, you kind of have a mix of two components or objectives, and here they are. So we have this overall loss function. Sorry, I mentioned at one of the very first modules of this course that we wanted to differentiate between loss, which is actually this lowercase l over here, and empirical risk, which is this big L over here. But I think over time, I kind of fell into the whole of what the community does, which is calling the empirical risk loss. It's kind of the average loss. Anyway, side note over. If we have some labeled data and lots of unlabeled data, then we can take our familiar supervised task loss, which is this first term. It looks very familiar to us. We have all of our x's and y's from our labeled data set. We compare our predictions, f sub theta of x to y. We compare them with our loss function. We take the average of those. That's our supervised task loss. And then we have our unlabeled data term. So we have a prediction here. F theta, we have x. We have some other loss term, which we'll talk about in a few moments. So this is a loss function of the data itself, and then we take the average of all of those over all of the unlabeled examples that we have. This is our unlabeled data term. So this is like a separate term we're trying to minimize. Again, we're trying to minimize the loss. So we're minimizing the supervised task loss of making our predictions correctly, and we're trying to minimize our unlabeled data term, which so far is mysterious, but we're trying to minimize this also. Maybe we want augmentations to be close to each other. We want them not to be far from each other, so we want their differences to be small. But generally, we want this loss function to be small. And then we have this hyperparameter, which is lambda, which came up a few times in the past also. This is just sort of a weighting term that just allows us to weight how much of our overall empirical risk comes from the supervised task loss versus how much comes from the unlabeled data loss function. So right now, here's a couple of high-level, just verbal representations of the unlabeled data loss. In pseudo-labeling, we can use the model's own high-confidence predictions as temporary labels. So the model makes its predictions, giving us pseudo values of y, and then we can kind of feed those pseudo values of y into a supervised prediction task. That's one example we'll see in practice in a moment. And then there's consistency regularization, which kind of fits this term a little bit better, which is you have a particular data point x in this space, and then you have some perturbations, t sub 1 and t sub 2. We can jiggle x to the left, we jiggle x to the right, and we want the representations of those modified inputs. So maybe x, these modifies to the left and right are just shifting the image to the left and right or rotating it or something like that. We want the representations for those slightly different representations of x to be very similar to each other. We want their differences to be small, giving us small values of LU that we can minimize. So, and then this list goes on and on. This is by no means exhaustive, and this is also very high level. We haven't really defined these, but that's fine. All you need to know right now is that we have a loss function on the unlabeled data itself. This tuning parameter, like all the other hyperparameters we have, matters quite a lot. If it's too small, and the unlabeled data, if it's too small, then this overall empirical risk function will weigh more heavily to the supervised task loss, and we're not actually taking advantage of all of this massive amount of unlabeled data that we have, because lambda is too small. If lambda is too big, then we're giving more weight to the unlabeled data. And then this can kind of be tricky. Like we have this gold ground truth labels y that exists in d sub l, but as lambda gets bigger, we're increasingly kind of ignoring it in favor of the unlabeled data, and we're getting most of our signal from the unlabeled data that we have. Maybe that's going to be good for us. We don't know yet. We always have to do the experiments, and we always have to optimize lambda appropriately on the validation set. So here's some self-supervised objectives. So that was semi-supervised objectives, where we have a supervised or labeled component and an unlabeled component, and we add them together in two parts, hence semi-supervised. Now we have self-supervised. Remember, self-supervised is getting an objective obtained from the data itself. So here's three examples of many linked to papers that are highly indicative of these approaches. So the reconstruction or denoising approach is one where we have an original data point x in our unlabeled data set. We take a noisy version of it. This noisy version is x tilde. There's tons of different ways of adding corruption to it, but imagine it's an image for now, and just imagine like randomly like knocking out pixels, making them black, or randomly modifying some pixels in the image as if you're shaking salt over the image. And then you have this model G. G is a model that knows the corrupted version, and it knows the original version, X, and it can compare those two, and it can learn a way to make the corrupted version more similar to the original version. It can effectively denoise the version that we explicitly noised ourselves, right? So this is kind of what I mentioned earlier, the supervised signal, because we know what the goal is. We know what the goal of denoising is. It's the original image. We know what the input of the denoising process is. It's whatever artificially noised data input we had, which is x tilde. And we can gradually learn a model, G, that learns to make these as close as possible. Makes the difference between the original image and the denoised version of the noisy image as small as possible. And the smallness can be represented by our familiar like Euclidean distance. And we can just sum over all of these for all of our data points in X. In self-supervised learning, we can assume, for argument's sake, that we have no labeled data at all. and all we're doing is just learning a model for that data. What's going on here is we're actually passing this empirical risk, big L, to another training objective, as its training objective to another model, F, which is going to learn a representation that minimizes this loss function. That's one way of doing it. We add a ton of noise to the data, we train a model to remove the noise, and then we can use that to as a sort of a pseudo signal to help us learn a representation of the data. So masked prediction is something we actually saw already. The classic example of this is the BERT paper, in which we randomly mask a word in a sequence of words. We have other words that are visible that we don't mask. We can ask the model to predict what word should occur in this position of this masked word, and we can measure its probability. We saw that earlier, that you can have a probability distribution over the possible words in that particular position. And gradually you want the correct word to give high probability, you want incorrect words to give low probability. So overall, this is a cross entropy. This is a form of cross entropy loss in which we're kind of making these predictions. And this is the mask loss, which came up in BERT. And then contrastive learning is relatively new for this module. Here we have a couple of things going on. We have this softmax function, which compares a couple of things. So first I'm going to just define what the terms are. Z sub I is the learned representation of a anchor example X sub I in our massive unlabeled data set. So we have an unlabeled data point X sub I. We have a learned representation, and through the process of contrastive learning, we want to get a really good representation, Z sub I. That's kind of like the hidden state or the embedding of X sub I. Then we take X sub I and we corrupt it in some way, or we transform it in some way. It's still label preserving of the same example. So maybe we crop a little bit, we mask a little bit, we can still corrupt it here. We can rotate it, we can twist it, we can do all those kinds of things. But the label should be the same. So whatever small change we make to Z sub I, the label should be the same. So this is a positive example. So all these modifications we can make to Z sub I should have the same label and should be very similar to the original data. And we see that up here at the top. So we have a high degree of similarity between Z sub I, the representation for the actual data, and the representation for the modified data, Z sub I plus. So this is synthetic data, but it should have the same label as X sub I. We compare their embeddings to each other, and they should be highly similar. Then we can have lots of other possible representations for other data points. I mean, here we're summing over all possible data points, J, in our unlabeled data set. Often we don't sum over all of them. But some of these should have representations that are further away from Z sub I than Z sub I pluses, because Z sub I plus are basically representations of the exact same data point, X sub I. So we want to kind of make similar representations more similar to each other, and dissimilar representations more dissimilar from each other. And then tau is sort of an extra hyperparameter. We call this the temperature parameter, and this controls how sharply the similarities are scaled in the softmax. So it's basically a way of just manipulating the softmax function. The sigmoid function, for what it's worth, also has this these parameters that allow you to stretch it out. So all three of these self-supervised objectives, which again is just a way of using the signal inside the data itself as a source of a training signal, all of them try to make Z capture something stable, reusable, and really indicative of the real nature of the data. So this is sometimes the whole purpose of machine learning itself. We don't want to make predictions. We want to take the data and we want to understand what's causing it. And getting these kinds of representations sort of helps in that approach. So the goal here, either at the end of this process or as just a pretext task to a subsequent fine-tuning task, is not to solve the final task directly, not to solve some prediction task directly, but just to learn really good features that potentially can make the final task easier, especially if you have fewer labels. So I have such a good idea of how my data work now. I have such a good representation of how X is produced that when I see a new version of X, I will have already totally understood it because of this pre-training, this self-supervised learning that I've already done. I already understand this new data point X so well that my predictions of it will be that much better if I start getting these labels Y, if they're available. Here's a bit of a reasoning sketch on consistency. So imagine we have two nearby points, X and X prime, and imagine they come from the same dense region of data. So imagine like a scatter plot of data points, X, and imagine there's a big dense cluster, or big dense region, and X prime are very close to each other. So if our unlabeled objective penalizes disagreement, then our loss function, this unlabeled objective, will be proportional to the distance between a prediction on X and a prediction on X prime. Okay, so we make a prediction from X, we make a prediction from X prime. There's a distance between these two things, and the unlabeled objective will penalize disagreement. So if predictions are further away, if there's disagreement, then that's bad. We want these things to be small. Losses want to be small. So if we have a decision boundary through this region, this dense region of points, then it's going to kind of slice right through data points which are very similar to each other, like one X and one X prime that are close to each other could happen to fall on either sides of this line. Sometimes there's countries that had borders drawn between them, and some side of the family was on the eastern side, others are on the western side, or the north and south, or wherever these boundaries are drawn. And they're split, even though they're similar to each other. And this kind of breaks this assumption. So, X and X prime are close to each other. A boundary is drawn between them, and we say, well, stuff on the left is west, stuff on the right is east, and then those labels will be different from each other. This distance will be large, and then this loss function will be unhappy. That basically is why consistency helps, and that's why it's been sort of implicit in a lot of the points I made previously. So this is not a guarantee in every data set. Sometimes dense regions do have different labels on either side of a decision boundary. Sometimes you do have to draw a decision boundary in these dense neighborhoods if you want to do like some kind of labeled prediction, some kind of supervised learning. That's one of the assumptions that we had to be wary of at the very beginning of this module. But the key intuition generally is that for many semi-supervised methods, at least, we assume consistency between clusters, we assume separation between clusters, and we assume better use of unlabeled structure when labels are sparse. So you have like two big groups of data. You have some labels here, some labels there, a lot of unlabeled data around in each of those clusters, but all of these unlabeled data points are in the same cluster as the labeled ones for this class, and all of the unlabeled data points for the other cluster are very similar or in the same cluster as the labeled points for the other class. So it's very easy to draw a distinction between these. So let's see some worked examples. This is a semi-supervised learning through pseudo-labeling. So here we're going to have handwritten digit classification. We have lots of examples. Well, not lots. We have a healthy amount of examples per class, and we want to imagine we only have 5 labeled examples per class. So we're mimicking the situation in which we have lots of unlabeled data and a small amount of labeled data. We want to know if the unlabeled data that we have can still help us in training. So what this code does, I'll let you go through it yourself, is it trains a classifier on the tiny label data set. So 5 labeled examples of 0, 5 labeled examples of 1, 5 of 2, of 3, or 4, and so on. So we have 50 data points in our original training set. We train a model using those 50 labeled examples. Then we take all of our unlabeled data. Again, this is technically we have the labels available, but we're pretending we don't for the moment. On all of the unlabeled data, we take our trained classifier, and we make predictions on all of those unlabeled examples. we look at the confidence of those examples, and then we have a threshold. Everything above this confidence we'll believe, and then we'll assign the label that the model gives us. And anything below that confidence, we'll say, well, the model isn't confident enough that this is a 7 and not a 1, so we're just going to leave this as unlabeled and not use it for training. Okay? But for the ones that the model labels with high confidence, says this is definitely a 7, believe me, trust me, bro. We'll take that example, put it back into the training set, and then retrain a model using the original 50 labeled examples plus all of the other examples from the unlabeled set that our classifier confidently believes that these are the labels for them. Okay? There is this confidence threshold that I mentioned. So this is another hyperparameter that we need to tune. If we have a low threshold, then the model essentially says, trust me, bro, for an increasingly large number of cases. The threshold is low. If the threshold is 25% and a model is 30% confident that this is an 8, then we'll believe that it's an 8. And maybe that's a very low threshold. It'll give us lots and lots of pseudo-labels, but it'll be very noisy because the lower we go, the less we can trust the predictions of this very, very simple predictor. If it's very high, if we only trust models, predictions that have a very high threshold, like only if the model is 98% or above confident, will we believe it? We're only going to get a small number of data points that we can add to our training set, but we'll really, really believe them. Okay, so we have this confidence threshold we have to deal with. Just a side note, I tried to mention this before, but all of that work we did in the early part of this course, dealing with the first principles of training logistic regression, it's coming back to us right now. Remember the logistic regression where we had this kind of a sigmoid function, and we had a decision boundary, I think we called it tau, and we can move it back and forth. And we had this very same discussion way back then at the beginning, and we talked about the same kind of challenges we're having now, about precision and recall at the time, if I recall correctly. So same scenario as always, but now it just happens to be in the context of using neural networks to make predictions on labels. Actually, I don't think this is actually we're just using plain old logistic regression again, but the lesson holds for neural networks as well. So anyway, the point here is we have a threshold we can modify. We can just sweep it. We can go from 80 to 90 to 95 to 99. In all of these cases, we have our initial labeled data set. We just took 5 random examples from each class. And it turned out that with a relatively low threshold of 80% confidence, we could add 848 pseudo-labels to our label data set and use all of that for training. And that kind of also is an example of the overwhelming. There's like an order of magnitude more data points which have pseudo-labels compared to ones with actual labels on them. So there we go. We have our validation accuracy on the validation set. We have our test accuracy on the test set. We have our test macro F1. And I also wanted to just look at the mean pseudo-label accuracy. So we don't always have this, but remember, for this particular example, I actually have labels for everything. It's just that I've pretended that some of the data is unlabeled, and I use that to kind of set up this whole setup. But technically, I can check, how well did that model trained on the original 50 label data points, how well did it make predictions on all of the high confidence predictions that we accepted into the training set. Hope that makes sense, right? So we say 80% threshold. These are all of the examples that I'm highly confident have their labels, but how correct was that process in actually assigning the correct label? Like, I'm super confident in this label, but is it actually right? That's what this last column tells us. Hope that makes sense. So, generally here, it kind of what you kind of expect to see happens. The higher your threshold, the more discerning you are, the higher your mean pseudo-label accuracy is going to be. You're dealing with examples that require a higher level of confidence, and the higher level of confidence in this case is actually correlated with a higher proportion of correct labels. So when you demand the model be 99% confident or better, then 100% of its labels in that small set is going to be correct. How small is that small set? It's only going to be 16 pseudo-labels. So in this with a 99% confidence level for the threshold, we've added 16 pseudo-labels to the original 50. Okay, so we have this kind of a scenario where we have lots and lots of pseudo-labels, like an order of magnitude at least, being added to a small amount of gold standard labels, but those labels are pretty noisy, relatively. And then we have a very tiny amount of labels added to our original labeled set, but those are really, really high quality labels. Okay, how do we actually do? Well, you can kind of see that here already. We actually do better, believe it or not, with in both validation and in test. We do, and sorry, by the way, if you wanted to optimize the threshold, we'd only care about the validation accuracy before we set on a particular threshold. We're not going to say, oh, well, you know, the best threshold, the threshold that gives us the highest test accuracy is this, therefore that's been our threshold all along. You don't do that. You say, well, this threshold gives us the highest accuracy on our validation set, and therefore that's our threshold going forward, and you use that on your test set. It just so happens that those two things line up in this kind of pseudo toy example. The best accuracy we get in both validation and test occurs when we add the most amount of data to our so-called labeled training set. Even if those labels are wrong almost 10% of the time, just the sheer number of them gives this scenario an obvious boost of over 5 percentage points. So there we go. This warning basically just summarizes what I mentioned before about this last column over here. So here we have our validation accuracy, this threshold over here, and the baseline validation accuracy, where we don't have any augmented data. And then you have the validation accuracy as you have higher levels of confidence. And here's the pseudo-label accuracy. This is just the teaching diagnostic. This is how accurate we are on the labels that we let the model label for us. So the more you let the model label things for you, as you get the higher, sorry, I'll say that again. As your confidence increases, as you become more and more discerning for what the model is telling you, that initial model, you're going to get accuracy on the pseudo labels that goes higher and higher, all the way up to 100%, like we mentioned a moment ago. But as you're more and more demanding of that initial model, the overall validation accuracy will actually go down. All right, so it actually kind of helps us a little bit in this case to have a threshold of 0.8. We're less discerning, but this gives us a lot more data. It gives us 848 more data points than this last one. So it seems to be an effect that the more data we have, the better we do. That's a really coarse solution, one that is a bit of a pet peeve of mine. People say, well, more data, the better, but that's not always the case by itself. Like I've tried to emphasize over and over again, machine learning is rarely that simple. So the moral of the story here is that higher thresholds in this example give cleaner pseudo labels, but a lot less of them, a lot fewer of them, I should say. Pardon me. Lower thresholds add much more data, but with more noise. I'd welcome you to kind of take this home and lower the confidence threshold to something crazy like 50% or 40%. That's certainly going to give you a lot more data. Eventually it's going to taper off, but you can keep on getting more and more pseudo labels with less and less confidence, but then see how that affects the overall validation accuracy. See if this thing can go any higher than that. See if this leftmost point on the blue curve can go any higher than that. So zooming out, a good analysis is not, hey, so semi-supervised learning worked, or in a counterfactual world, semi-supervised training failed. You have to say why. This is not, again, like all these examples usually show you positive wins. It makes sense pedagogically, like why would I be showing you this technique if I didn't get better performance out of it? But the one thing to remember in the real world is that your experience is not always going to be as rosy as it seems in these slides or on social media or in research papers. You need to kind of scratch the surface and answer the why question. Why does it work? Well, it works because we had a nice balance of thresholds and labels and noise and and the nature of the data. So some combination of this data set, the task, the threshold, everything gave us this particular scenario. And if something changed, it would be like pulling out a tile from a Jenga tower. The whole thing can come crashing down potentially. Okay, so I mentioned all of these points a moment ago. I don't need to go through it anymore. Just to reinforce the idea that we're scientists. Even when we're not actually doing like active science, you need to be curious and you need to double check your conclusions, and you need to kind of keep on asking why and be curious. It works in that example, but you can break that example fairly easily. This is a bit of a zoom in. A pseudo-labeling of this type, using a model to label unlabeled data points, kind of gives you temporary labels. Consistency regularization, in contrast, asks the model to give similar predictions under small perturbations. So this is just a side note. I should have included a citation here also. But basically what this code is doing, this unrun code is doing, is it's doing some kind of augmentation on a data point x sub u. And augmentations are stochastic. So when I run this function on line 2 and line 3, it's actually giving me different perturbations of x sub u, which is giving me different predictions from the same model on lines 2 and 3. So my prediction P1 and P2 are going to be slightly different. So now I can make like a supervised, I can have cross entropy. I can compare the prediction made on data point x sub l with the label on point L, which is y sub L. And then I can check for consistencies. I can look for the difference between P1 and P2. And I can want these things to be small. So here's the difference, here's the square, and the sum over all of these possible values and their mean is computed here. This is the consistency. So I want the model that's making predictions on label data on line 5 to also give me labels that are consistent with each other, that are small, given tiny perturbations, which I call augmentations here, which gives me different predictions, potentially different predictions P1 and P2. I want P1 and P2 to be as close as possible to each other. Then my overall loss is the supervised loss on line 5, and a weighted version of my consistency loss from line 6 from the unlabeled data. So I'm doing something on the label data on line 5. I'm doing something with the unlabeled data on line 2, 3, and 6. And then I'm weighting according to my lambda, which is not defined in this pseudocode anyway. And then I do my backward processing. I do my optimization. I zero out my grads. Everything else I have to do in my normal training process. This assumes I'm doing torch right now and neural networks. Anyway, this is pretty much an exact example of how we defined semi-supervised learning at the beginning of this module, as a weighted sum of a supervised component on one subset of data and an unsupervised loss on another, on the unlabeled data. Here I'm not inventing hard labels. I'm not saying label my unlabeled data points and then just add them into the labeled data set. This is a completely other way of semi-supervised learning. It's just coming up with labels on the fly and making sure they're not too different from each other, and then it throws them away. I'm not going to use them to learn a supervised task like I did a moment ago in my worked example. Okay, this is just here to emphasize that there's not one way of doing semi-supervised learning. There's many. So now the second worked example, which is self-supervised learning, the other side of the coin for most of today's module. So now we're going to have a question, which is instead of using unlabeled data to label the task itself, we're going to ask, can unlabeled data help to learn a representation that works better with few labels? So in this example, we're going to ignore the labels entirely. We're going to train what's called a tiny denoising autoencoder. This is something that is going to come up in 3152 or slightly more advanced versions of machine learning courses at this university. So we're just mentioning it now briefly, and then you'll see it later in future courses. But it's a way of an autoencoder is an encoder model, and it's an encoder that learns itself. Actually, we've seen examples of autoencoding in the self-attention and encoder components of the previous modules, the previous recent modules. Anyway, we'll train a tiny autoencoder that learns to remove noise from its inputs, like I mentioned a few moments ago, earlier in this deck. And we'll do that on training images. We can assume all of them right now are unlabeled. Then we're going to take the encoder representations as these features. This autoencoder has learned a really good representation of whatever's underneath that noise. And then finally, we're going to take a small supervised classifier on a tiny labeled subset as before, as a previous example. Okay, so we're not going to be using the unlabeled data to produce any labels at all. We're not going to say this example X should be labeled as a 7 or an 8 or a 9 or a 0. We're not doing that in either of the ways we mentioned in the previous work example. We're just learning from the unlabeled data entirely, getting a really good representation of the unlabeled data, and then quickly we're going to use the representations learned from the unlabeled training process to do our predictions on the labeled subset. Again, we have subtleties here, just like we had subtleties in the previous worked example. We're going to have to corrupt the data. We're going to have to add noise to the data that we can then denoise in the self-supervised phase of learning. If it's too weak, if we add a very light amount of noise to the original data, then it's very easy to regain the original data, and it's not hard to, it's very superficial. We haven't learned any deep structure in the data. If the noise is way too strong, then we wash away all of the actual information in the actual unlabeled data. We've kind of washed away or hidden the useful structure that we want to learn. So we're at a loss there also. Again, as usual, I welcome you to, this code is a bit, it's a bit long, and I have a habit of walking through this a bit more than I want to for these videos, but it's pretty self-explanatory, and if needed, I can explain parts of this in class. Anyway, so we went ahead and did that. We went ahead and did exactly what I mentioned a moment ago. This is the tiny denoising autoencoder. This is a neural network now from Torch, which is a linear layer followed by ReLU, followed by linear. And then we have another layer, which is the decoder, encodes and decodes. It's forward predictions and encodes. So it basically produces, it takes in images and it produces images. And all this is done on device. We have a mean squared error loss. So it's kind of doing a regression on images. So it's not making a classification. It's, again, producing something in a continuous space. In this case, H by W, things in continuous space, the image itself. Anyway, so my point is that we add noise to the data. Here's where we add noise to the data. And then we do the training for autoencoder to remove the noise. So we want to learn the loss is the difference between the actual inputs, XB, and the reconstructions, recon, which I obtain from my autoencoder, which I'm trying to train to remove the noise. And this gives me an autoencoder which is very good at removing noise from things, which is helpful on its own. Sometimes you want to remove noise from a signal or from a video, so this will be good on its own for a variety of tasks. But eventually I want to use this for classification. So I take my autoencoder after I've trained it using self-supervised learning, and then I want to make a pipeline in which I take the representations of my original data, but encoded using my autoencoder. So the autoencoder, which is really good at removing noise because it understands the data so well, is going to now take all of my labeled data, and it's going to represent the labeled data X in terms of the representations that the autoencoder learned. So it's like I know what this is. I know what I'm looking at. There's all this structure. There should be a loop over here. There should be an intersection over there. There should be a point over there. I'm really good at understanding this image, and so we are then going to use that representation in a simple classifier. This is a logistic regression, which now instead of having raw images as inputs, it's taking the representations from the autoencoder as inputs, and it's a logistic regression with 4,000 iterations. You can again play with this to your heart's content, and it learns its fitting here on line 75. And then I'm kind of done. I've done the autoencoding, so I've learned really good representations of the data by learning to denoise noisified versions of the data. I've taken these really good representations of the data, and then there's a function now. The autoencoder is kind of like a function which learns good representations of the data. I obtain really good representations of all my labeled data. Again, that's 5 examples of 0, 5 examples of 1, 5 examples of 2, and so on. And now I'm going to train a supervised classifier just on that very tiny little data set of labeled examples. Okay, so I'm not labeling some of the unlabeled data and adding it to my labeled set. That would be one form of semi-supervised learning. I'm not trying to learn a labeling task loss and a dissimilarity loss, consistency loss at the same time. That would be semi-supervised learning. No, I'm doing self-supervised learning first. I'm learning how to represent X. And then once I've learned how to represent X, I'm so good at that I can take only a tiny bit of data and make really good predictions on that. So I'm still doing supervised learning at the end, but on representations that I know are really good. And these are the results I get. So I only have 50 labeled examples now because I'm not augmenting my labeled data set at all. Given just the raw pixels, I get a validation accuracy of 81.4%. And by taking X, passing it through my self-supervised encoder and getting those features, and then passing those features to a logistic regression, trained again the same hyperparameters as row 0, I get an increase of about 3 percentage points in validation accuracy. I also get about 3% improvement on test accuracy and about 3% on F1. 3% is neither good nor bad on its own, but it is substantial enough that it's noteworthy. We've won the game by adding autoencoder features to this very simple task. Here's just a quick view of what we did during the autoencoding. So we have our original representations of our digits here, 0, 1, 2. Even I would have trouble looking at this and doing correct classification. I think these ought to be 3s, just given the sequence here, but I'm not sure. Looks like a 5, looks like a 7. Anyway, you can see how hard it is for the neural network and then logistic regression. Anyway, sorry, so we have the original data on top. We've added noise, on line whatever it was a few moments ago to the image. You can see here this pixel is a lot darker than it is over there. This pixel over here is darker than it was over there. So we're adding noise to these images. But then the autoencoder is able to reconstruct the original image. So like this noise that I added kind of automatically in this middle row is now gone. The autoencoder has learned to remove it. The reconstruction is very similar to the top row. In fact, that's what the autoencoder is learning to do. It's learning to make its reconstructions as similar to the top row as possible. It's not perfect here. So here the reconstruction actually seems to add a little bit of noise in this little gap over here that doesn't exist in the noisy version. But generally, on average, doing this kind of learning how to do this reconstruction well gets us a representation for these images that are helpful for us to do the supervised task later with a small amount of training data. Here's just a PCA view of our features. So here's just colored a bunch of the digits in our data set. This is the original data, so obviously the 5 individual cases that I extracted as the labeled set are to differentiate it here in any way. But we have the original data, we have the self-supervised encoder features, and generally not much you can say about this, to be honest. To be honest, I had a tough time getting these numbers to get a win for the autoencoder, which I'll mention in a moment. But if I was one of those people who wanted to spot things that helped my story, I could find instances where maybe this turquoise set, which is the 9s, seems to be a bit more differentiable from the 3s in the self-supervised encoder features than on the original pixel features. But then I'd remind myself that that's just me trying to find the signal I'm looking for. And that's one of the human fallibilities that we keep on coming back to, which you and I are trying to avoid to be good scientists. We want to double check. We want to catch ourselves trying to pat ourselves in the back and finding successes of that type. So some like interpretation or caveats. So why did that help? Why did learning that denoising autoencoder help us? It forced us to represent a stable visual structure rather than memorizing things in the labeled data set, especially a very tiny labeled data set. So the overfitting or memorization seemed to be less of a problem because we didn't have any labels to begin with. The downstream classifier that we end up training eventually on the labeled set, given the encodings that we obtained from the self-supervised pretext phase, it works in a space that may already be fairly differentiable in terms of strokes, shapes, and local patterns. The PCA view I mentioned a moment ago is diagnostic. It might help us find severe problems, but what I just did a moment ago also by trying to spot signs of good fortune might not be doing good science. I have to mention that improvement is not always guaranteed. Like every other thing I'm mentioning here, it's easy to get wins from each of the things, the tools or methods we've added at every stage of this course. And indeed, the transformer, which is kind of the pinnacle of where this course is ending up, is just a fantastic tool. And it solves lots of problems from all of the previous tools that built up to that point. But it doesn't always work. It's very easy to get mistakes. And a lot of the challenges you can obtain with these models are solved by earlier models. And a lot of the lessons we learned using simpler models like logistic regression end up coming back to us even now and being relevant in these more complicated models. So anyway, the main messages I want to mention here are a poor pretext task, like the self-supervised phase, can sometimes learn the wrong things, the wrong invariances, like the wrong structure in the data might not be helpful for me later when I'm doing prediction. It happens to be helpful here because I have a very simple digit prediction task. So on easy data sets, raw pixels may already be enough, and indeed on this, the raw pixels here are already doing a pretty good job. In the code, which I kind of walked over quickly, I had to set hidden dimensions and latent dimensions fairly highly, and I had to make the noise standard deviations fairly low in order to get these numbers. I'm sure I could fiddle with these numbers a bit more and get more stark differences between the raw representations of the data and the auto-encoded representations of the data. But indeed, it's going to be not hard for you to fiddle with these hyperparameters and end up with situations where the autoencoder actually makes things worse for the eventual supervised training. So I'll leave that to you as an exercise. The main goal here, of course, is that the pre-training distribution in all of the unlabeled data should resemble the downstream one in meaningful ways. And if you have a big cloud of data where all of these data points ought to have very different labels, then it's going to be hard for you to draw boundaries between these labels, and that's going to break one of the assumptions we had at the very beginning of this course, which kinds of would suggest that this particular instance of self-supervised learning might be a bit not naive, but a bit hopeful. So a few final thoughts in this, the last really contentful course module. So we have a landscape of methods and some patterns that we need to memorize. There's no microscope here. We have pseudo-labeling. This is where the model's own predictions that are confident are a form of supervision. So the objective here is like add temporary labels on unlabeled data and pretend they were original labels. And this is kind of like bootstrapping the task. It's like we want to have supervised labels, we don't have them, so we're going to pretend we have them. One of the risks is that it can confirm early mistakes. So if that model that's trained on the tiny amount of actually labeled data is really bad or makes a particular kind of mistake, the pseudo-labeling is going to amplify that kind of mistake. Consistency regularization, which is that kind of side note we mentioned at the bottom of example 1 on the semi-supervised learning. We want to make perturbations to the data and then make predictions across these permutations and then ensure that we're getting the similar answer. So we want, if it's the same example, just from slightly different views, rotate it a little bit or maybe some noise added to it, and then a prediction is made. Those predictions should be very similar because it's basically the same data point. A risk is if we make bad augmentations, if we augment things crazily, or if we augment things in ways that aren't ecologically valid, then the predictions made are going to be all over the place, and then the assumptions are going to be wrong, and then that second term in that labeled loss and the unlabeled loss is going to be garbage, so to speak. Masked prediction is where we hide part of the input, as the name suggests, and we try to predict the missing piece. You can think of this as filling in the blank. This is extremely popular in language modeling, for example. Now, normally this actually works out pretty well. Sometimes it doesn't match the downstream needs very well, though. Sometimes just merely predicting what word is missing is not going to capture something deeper or something much more semantic in the data, something that really lives only in the label in some higher level tasks. So just doing this sort of auto-encoding is not going to help you very much. But it turns out if you have enough data, often it does. And then we have contrastive learning, which we just kind of brushed over quickly. That's where we have so-called positive and negative pairs. I'm going to talk about this in a few moments, so I'll just touch it lightly now. This is where we pull matched views together. So it's kind of similar to consistency regularization. These are two views of the same thing, so the representation should be close. And this is something that's different. We want this representation to be far away. This, somewhat darkly, is called who belongs with whom. That's kind of I don't like saying that really, but there we have it. Who belongs with whom is what this contrastive learning is kind of trying to do from a very abstract point of view. I should come up with a nicer way of saying that. So again, there's risks all over the place. The risk here is several risks, one of which is that these views of the same thing, just like in the contrastive regularization, can like break a certain assumption and then the whole thing falls apart. How we find pairs can also be a problem. We can collapse representations too much, or we can eject somewhat similar data points that should be somewhat similar. We can force them to be really, really distinct from each other in terms of their representation. And that can be bad also. So all kinds of things can go wrong with contrastive learning in theory. So just a side note about pseudo-labeling versus consistency regularization. Both of these are semi-supervised. I could have mentioned this at the end of example 1. But where they're using unlabeled data differently. So pseudo-labeling turns a model prediction into a temporary hard target. Usually this needs a confidence threshold like we've seen. It can give good gains when predictions are mostly correct and the initial model is good. Consistency regularization does not require you to say this is definitely this label. You can just make lots of labels while you're computing your loss functions. They just have to be similar to each other. We want stable predictions. We want to preserve the labels given perturbations which should preserve the labels. So an image of a tumor, for example, should still be an image of a tumor, whether it's shifted to the left or right slightly or rotated clockwise or counterclockwise slightly. The label should be preserved. So therefore, if the predictions are way different, that's bad. So we want the consistency to be minimized, or the consistency to be maximized by making their difference minimized. Often this behaves more gently early in training. This is also, this makes sense sometimes, but not all the time, so I take this with a grain of salt. A useful rule is pseudo-labeling basically says, I think this is class 3, so I'm going to pretend it's in class 3. Consistency just says, well, these data points are similar, so they should have the same label. I want to compare masked prediction versus contrastive learning. So these are both self-supervised methods, but they produce their internal representations, which we've mostly been calling Z, differently. Masked prediction, again, hides part of the input, predicts what's missing, and then if it's really good at predicting what's missing, it'll have to understand the nature of words, the nature of grammar, the nature of meaning in a very deep way. So it totally understands language with these very deep transformer models. Indeed, BERT is sort of the canonical example of masked prediction being really helpful in a variety of contexts as a self-supervised method. This is masked prediction. Contrastive learning creates two related views of the same example, pulls those related views together, and pushes unrelated examples apart. So just to make sure this distinction is clear, this is redundant with what I've said previously, but I just wanted to hammer this home for some reason. Hint, hint. So masked prediction learns from reconstruction pressure, like I need to be able to reconstruct what's missing. That's masked prediction during self-supervised learning. Contrastive learning says, well, like if I'm making small changes on the inputs, I want my representations to be similar. So this is more about similarity, like the similarity of representations. That's where the pressure comes from. Again, apologies for the visualization here. We have an example X. We can apply an augmentation to X. I can actually apply a few of them. So we apply augmentation T1, which is up here, believe it or not. And we have augmentation T2, which is down here. So this is like a view to the left and a view to the right of the same thing, X. We obtain embedding for the transformation 1, and the transformation 2 is down here. And then we have a other example, which is not X, and we get an embedding for that. We want the embedding for not X to be far away from this embedding from like one particular view of X. We also want, so this dash thing means I want this representation to be far away from each other. The solid line over here indicates that I want the embedding for transformation 2 down here to be similar to the embedding for transformation 1 up here. I want these to be similar to each other. And that's basically it. You can have more than one other example. So here's like example X. I have two views of it. And then I have example, for lack of a better word, I'll call this A. I have view 1 of A, view 2 of A. Their embeddings are very similar to each other. I have B, which is not A, and I have an embedding for it. I want it to differ from my representation of A. And I have another example, C, with its own embedding. I want its embedding to be far away from my representation of A also. Okay? So this is going to make my possible views of A all very similar to each other, and my view of things that are not A to be more and more far away from each other. And that's basically it. Here's a little code sketch. Here again, augment is that same pretend function I didn't define, which is just like a stochastic view of, like randomly giving slight modifications to input data, X, in a batch. X1 will be one view, X2 will be another view, Z1 will be the encoding representations of X1, Z2 will be the encoded representations of X2. I normalize these, because you generally have to do that. And then I can compute the similarity of these through the dot product. This, again, this at symbol is a relatively new addition to Python that allows you to do dot products in lists. And then I divide these by tau, which is one of our, we saw that softmax function. Tau was that parameter that basically told us like how much we're measuring similarity. It's a hyperparameter. And then we compute the contrastive loss here. So, I mean, this is, again, redundant with what I said earlier. I just wanted to have it in code because it's nice to have code and math views of the same thing. In fact, this is the first time I think I thought of this, is that we have a concept which is sort of hidden. We have one view of it, call it x sub 1, which is a particular view of that concept, which is math. And then we have another view of that thing, which is another perspective of that same concept, which is code. And we want the code view and the math view to be very similar to each other because it's the same concept under the surface. That's a funny thing that just came to mind right now. Just a bit of luck. But that's essentially what we're doing here. I wanted to mention a bit of a bridge. So you have one more assignment due in this course for those of you who are actually taking this course. Assignment 4 is posted. It's a mask prediction task, this BERT-like pre-training. So there's some worked examples above that are basically image-based because they're small and self-contained and they're easy to put into a slide deck like this. But this lab is, the lab is connected to this module, or the assignment is connected to this module, but it's text-oriented. So you're going to have to do like denoising or next token prediction on text. And then you're going to have to reuse the encoder for this downstream classification task and compare pre-trained representations against just training from scratch. So the image autoencoder example we saw in this module should be, like, again, one particular view of an approach for self-supervised learning, which can also be applied given text. I wanted to mention that. I also wanted to mention that BERT and GPT and a lot of its siblings all basically use this sort of an analog of this autoencoder to represent things. Although technically GPT is decoder only, it still has to obtain an internal representation for what it's about to predict. So I just wanted to make a bridge between this module and the other material that we're providing in this course. Oh, how long ago did that happen? I have a couple of views here on my computer, and hopefully that wasn't that long ago. I have been waving my hands around a lot in a very illustrative manner, and hopefully that was shown on the screen. So I also wanted to mention reinforcement learning. So this is a machine learning class, and learning appears in both machine learning and reinforcement learning. So you might ask yourself, where is reinforcement learning, especially given that we're just wrapping up the content of this course. So reinforcement learning is sometimes like shown on the same spectrum as supervised learning and unsupervised learning, but it's really an apple to those oranges. It's really different, even though a lot of the mechanisms and a lot of the risks under it are very much the same. Reinforcement learning is different from self-supervised and semi-supervised learning and supervised learning. And here's some classic papers. These are, RL goes way back, so these are relatively classic papers or treatments of reinforcement learning. But just to draw some comparisons, semi-supervised learning, the extra signal comes from unlabeled examples in the same task. In self-supervised learning, the signal is generated from the structure of the raw unlabeled data itself. And in reinforcement learning, the signal that we're using to learn about the world and how to behave in it comes from rewards that we obtain by interacting with the world. So instead of having just this is our input, this is our output, and learning functions between these, learning representations of data, this is much more agentic, I guess you could say, RL is. And it's about an entity interacting with the world and getting feedback according to some measure of success. Measures of success or utility functions in reinforcement learning are somewhat similar to empirical loss in machine learning, but they're also different. So these concepts are siblings of each other, but they're different. And including reinforcement learning deeply in this course would be unfair to reinforcement learning and everything else. Fortunately, there's a really fantastic course at Dalhousie, CSCI 4250, which focuses on deep reinforcement learning specifically. So even though there's some similarities, RL doesn't really fit here, but I wanted to mention it just in contrast with everything else. And I encourage you to take CSCI 4250 and other machine learning courses at Dalhousie. So to wrap up this module, I should say, we're not going to wrap up the course just yet. So for this module, the evaluation question is not just like, did the model's score go up according to whatever metric? It's, did the unlabeled data help because of the reason we thought it did? Like over and over again, we're using semi-supervised learning or self-supervised learning, and we want the supervised part at the end to get better accuracy on whatever its task is. But that's not enough. We need to make sure that the unlabeled data is actually helping for reasons we understand. Otherwise, the more we don't understand the model, the harder it is to hold it onto its reins. There's this other work over here, which I encourage you to check out, which basically looks at some checks for this semi-supervised learning algorithms specifically, although a lot of this also applies to self-supervised learning. So check validation accuracy for any kind of thresholds that you're using. Thresholds and hyperparameters come up a lot in this module, so using validation to just check those is always important. Test performance, like always, is only going to be used once. Even though we're doing like more phases now, test is still something that's held out, it's sacrosanct, and it's only used at the very end. Ablations against supervised only baselines is a helpful thing to do. Thresholds to not just your threshold or your corruption or your augmentation is important, but sensitivity to any kind of differences that you obtain through these methods is also going to be important to check. And ensure just to do the data science thing, make sure that the unlabeled data comes from the same population, lives in the same feature space as the labeled data, that there's no unintended leakage from the labeled set to the unlabeled set or vice versa. Set up your lab as cleanly as you possibly can, given what you've learned in this course and outside of this course. So when the labels are scarce, variance can be very high. because you only have a couple of measurements so far. So if you just do one run, if we just did what we did in example one and learn a model and very quickly use it, that can be misleading. One thing you might want to try is you might want to redo the experiment from example one, but do like some kind of bootstrapping and do some like frequent samplings of that small label data set, and see if you can get like the variance for the predictions to decrease. So some common failure modes for across these methods of learning. We talked about confirmation loops and pseudo-labeling. I mentioned this earlier. If that very tiny label we trained on the tiny amount of label data initially learns something wrong, then when it labels all of the unlabeled data, that wrongness is going to be amplified. And then when you reintroduce those confident predictions into your training set, the wrongness is going to dig in. When you're doing augmentations, you can break in variances. So like if an augmentation changes the label, but you're pretending that it doesn't, that will be a possible failure mode. If the pretext task is not helpful for later, that can be a problem. I mentioned BERT, for example, just predicting the word that's missing. Like seems like it would be very disconnected from most natural language processing prediction tasks. Like, is this tweet happy or sad? Is this medical note an example of this particular disease? But believe it or not, usually that works very well. So that's a pretext task that you wouldn't think would be closely aligned, but is. This point actually talks about the reverse, which is where you think this pretext task is going to really help you get good representations for your eventual predictions on a small amount of labeled data, but it really doesn't. Like whatever you're doing beforehand to learn good representations, those representations aren't going to help you. Again, the distribution mismatch, so the unlabeled data coming from different sources than the label task. This is a whole field of work about distribution shifts in machine learning, and it's probably going to come up in a few of our fourth-year courses at Dalhousie, talking about distribution shift and responsible AI. We'll put that aside for now. It came up kind of at a high level in this course and today, and just keep that in mind as some topic that you want to learn about more in the future. So again, the unlabeled data, you're assuming often that it comes from the same source as the label task, but this isn't always the case. And you can easily generate visuals like we did today, and you can generate much more convincing representations than what we did today. And a convincing representation can convince a human with cognitive biases to believe whatever they want to believe in that representation. But again, humans are easily fooled, and those pretty pictures doesn't mean true pictures. So our ethics and risks. These methods rely on lots of unlabeled data, which can introduce some unique practical risks. Bias amplification, so pseudo-labels, may be more accurate for already well-represented groups. So that model that's making its predictions and producing these pseudo-labels, if it learns to be biased on a small amount of labeled data, then the bias could be applied to the unlabeled data. Second, privacy. Unlabeled doesn't mean harmless. So even if you don't have a label, it doesn't mean that raw text or images or logs or like quasi-identifying information can still be sensitive. So just because the label is missing doesn't mean PHI, or personally identified information, PII, isn't there. Representations can also be harmful. We talked a little bit before about how representations of words can sometimes, like the embeddings can sometimes emphasize representations that we don't want, can harm people. And then robustness and misuse, so high confidence can appear to be authoritative, but like I mentioned earlier, confidence is not correct. Confidence is not correctness, so you have to be able to differentiate these two concepts in your mind. We have simple mitigation. So as always, comparing subgroup performances where possible is something you can do. Documentation is our perennial mitigation against these kinds of problems. Inspecting failure cases is important, not just giving averages like we did today, but looking at particular errors and seeing like why these errors occurred. Keeping clean supervised baselines and avoid claiming any kind of magic like silver bullet performance is not good. you always want to couch your predictions in caveats and context. Context is king, as they say. Or context is the monarch, as they say. So why does all this matter? So ML, modern machine learning systems usually use some form of pre-training on a huge amount of unlabeled corpora. These black box API-driven corporate LLMs tend to be pre-trained on a ton of unlabeled data obtained from everything you do online and everything your loved ones do online and everything that's ever been written by people these companies didn't pay, et cetera, et cetera. So there's a lot of unlabeled data used in a pre-training process. And then those embeddings were then adapted somewhat on a little bit of task-specific supervision, which these companies can obtain. This is the story for open models like BERT and Llama and others, but also the closed source ones. Clip, I'll put a link here before I post these slides. The Clip and Wave2Vec, which we mentioned previously as a transformer model, does a lot of self-supervised learning before it's fine-tuned on a supervised task. So a lot of the cutting edge uses either semi-supervised learning or often these days self-supervised learning. Here are your quick checks. And I'll thank you right now. I've introduced a couple of answers in this particular deck, which I'm going to zoom over quickly. But you should do these questions before you watch the rest of this video because the answers are going to pop up very quickly. Here are some of the all the references we had in today's lecture. Thanks so much. That concludes the main content of this class, but I'm going to have more to say about the class as a whole. This is probably going to be only done live in person in class and not posted online, but I'm going to have some messages about machine learning generally, which I'd like to convey and to really wrap up this course. So until then, thanks so much for watching and see you next time.